So the bromination of an alkane is a limited synthetic utility. It has to be used on an alkane. It needs to have a difference in reactivity for one carbon, and it's best if it's bromine is the reagent we use. So we can brominate it to add the bromine on the most substituted carbon, and then from there we can get into both the substitution and the elimination that we will continue on with in this section. Hello again, everybody, and here we are in the part 2 of substitutions and elimination reactions, and we're talking about substitutions. And in a substitution reaction, there are 2 distinct pathways that we can see the reaction going via. And as we look at the 2, there's on the first one we come to an SN2 mechanism, where in an SN2 it stands for substitution, nucleophilic, bimolecular, and in the rate determining step of the reaction, the nucleophile, whatever the nucleophile is, has to come in and attack the carbon that has our leaving group on it, kicking out our leaving group to give us our product. So in the rate determining step of this, which since there's only one step in this example, it has to be the rate determining step. The nucleophile comes in, the leaving group leaves, it all happens at once. The nucleophile and the compound with the leaving group have to come together to form the product. So bimolecular. In the second example, we see down below we have the SN1, and in an SN1 it is a substitution nucleophilic unimolecular, where in the rate determining step, in this one, it is the loss of the leaving group to form the cation. In this step, the only thing that matters is our concentration of the compound with a leaving group on it. The amount of nucleophile we have does not matter because it is a fast step. The rate determining step is the first step, the formation of the cation. Once we form the cation, then the nucleophile adds in and we form our product. Hey, now remember, the cation is sp2 hybridized, and it is trigonal planar. So that helps with how the reaction can go as we're going along. So from what we've talked about already in Org 1, which of these compounds below, the primary leaving group or the tertiary leaving group, is going to be best for each of the reactions? And we remember that a tertiary cation is the most stable, so this will go best via an SN1 mechanism, and the primary one will go best via SN2 because in the SN2 the nucleophile has to come in, kicking out the leaving group. So sterics will play a role in the speed of an SN2 mechanism. So here we have 2 reactions. We're going to draw the mechanism for each. In the SN1, remember what we showed before, we have to form the cation, and then to that cation our nucleophile will add, forming our product. So in this we have 2 steps in the mechanism. The first one is the rate determining step, so it's going to take much more energy, and then form the intermediate, and then from the intermediate we'll go down to form our product. So we have our tertiary iodide and tertiary chloride. Here we have our cation, and then this is transition state number 1, and this is our transition state number 2. Sorry, I put those backwards. Number 1 and number 2. So at transition state number 1, we are breaking the bond between the carbon and the chlorine, so that bond is lengthening out. And then in the transition state number 2, we're forming the bond between the iodide and the carbon. So it will be the exact opposite of what we have for the first one. And we'll draw those out on a separate page in just a minute. And then down below in the SN2, it takes less to write because all we have to have is the nucleophile come in, the leaving group leave, all in one step to get us to our product. So the reaction where we have our starting chloride and we form our iodide. Here we have our transition state, and in the transition state we have the iodide coming into the carbon, the chloride leaving, we have our hydrogen, and our alkyl chain. And this is our transition state for this mechanism. And we know the iodide is coming in with a negative, so when it starts to form a bond with the carbon, we'll have a partial negative, and when the chlorine is leaving, it'll have a partial negative. So the overall mechanism is the nucleophile comes in, the leaving group leaves, and in the transition state for this, we have the partial bond between the iodide and the carbon, and a partial bond between the carbon and the chlorine, with our hydrogens and our butyl chain all off of that carbon in roughly a planar grouping straight down the center of the molecule. Let's go back up to the top one. Maybe I can fit in the transition state up here for the first one without it looking too bad. But what we have is this, where we have the bond lengthening between the carbon and the chlorine. The chlorine is leaving with a negative, so it'll have a partial negative. The carbon is forming a partial positive, and then we have that. And then the transition state for the second transition state is just going to be where we replace the chlorine with the iodide and draw it. So it would look something like this, with a partial negative on the iodide and a partial positive on the carbon. Now for this substitution reactions, there are some guidelines you need to know for going through all of these, and they're all on this page. Okay, in the first one, the strength of the base or the nucleophile determines the order of the reaction. A strong base, strong nucleophile has to be an E2 or an SN2. A weak base or a weak nucleophile is going to be an SN1 or an E1. Okay. Then the second one, primary halides, are primarily going to be SN2 reaction unless you have a strong base that is a very bad nucleophile. And then the tertiary halides, if you have a strong base, they're E2. If you have a weak base, they're going to be either an E1 or an SN1. And then secondary halides, depending on what you have, can either be SN2 or E2 or SN1 or E1, and you really have to be careful what you have going on. If you have a strong base, strong nucleophile, it'll be a 2 mechanism. If you have a weak base, weak nucleophile, it'll be a 1 mechanism. And then the next one, polar protic versus aprotic. The polar protic reactions favor an SN1 mechanism. Polar aprotic favor an SN2. High temperatures favor elimination. And then some bases favor substitution if they're small, like methoxide, whereas some favor elimination if they're big, like T-butoxide. So we have to be careful what we have available to us to decide what can happen.